So welcome to the episode 3 of our story of Photoelectric Effect. And in the previous episode I talked about Hertz, who was doing a wonderful series of experiments to see if electromagnetic waves actually exist as predicted by Maxwell's theory, and Hertz himself was crucially involved in reformulating Maxwell's equation in a different manner, in a different style, which are much more symmetric and popular nowadays. We are all working with that. And during those experiments, the basic thing was this, where a primary circuit created some kind of a spark, and that spark controlled the LCR oscillations, and from there pulse of electromagnetic wave was generated, and those electromagnetic waves could travel a good distance in his lab, where the secondary receiver loop was there and created sparks there. And the adjustable length here, that was his meter for how strong the electromagnetic radiation is coming. This wave is coming from the primary circuit, and this adjustment of this length, that was the kind of his tool. So length of the spark, length of this gap, that he could adjust using that whatever mechanism he has put here. And how much is the maximum length that a spark can jump? That gives me the idea of the strength. And then when he encloses this receiver circuit to be able to see it more clearly, and then he finds that shielding sometimes reduces the spark length, and ultimately he finds that it is basically the ultraviolet component from the spark itself that is doing the trick. So although this was a side mention of this phenomena in his main paper, where he produced this electromagnetic waves in the lab and detected a very, very important and very, very crucial piece of experiment, which has really changed the whole perception of the whole technology. But then, this particular effect was so interesting to him that he took out few months, at least, from his main research course, and pursued this. And he created his own apparatus once again, specifically to study this and why this spark length reduces when ultraviolet is there. First to confirm that yes, it is there, and then to see the conditions in which it is there. And I'll just show a page from Physics Today, volume 42, where he used certain apparatus which is put in some museum, and you see what kind of apparatus he has used. In fact, it was a big 16-page paper in German, and I could not get the original of that, but the description of that is available at many places. Just see the apparatus. So this is the apparatus, the original apparatus, and the article says that Hertz used this equipment in Karlsruhe in 1887 to study the effect of light on the spark, jumping a gap between two electrodes in an evacuated bell jar. So this is in this Deutsches Museum, Munich. Alright, so you can see here, this is that gap, and the spark is produced here using some external source, and then between that source and this bell jar, this evacuated bell jar, he puts varieties of shields, and then studies that what kind of light or which part of the light creates this change in the spark length, and so on, so on, so on. So this particular study was devoted to this aspect. Alright, so the description of this is here. Description of this is somewhere here. Yes. So it says that to clarify how light enhanced the sparking, Hertz used poles of copper, brass, aluminium, iron, tin, zinc and lead. See, if he has taken some problem in hand, he will do a very good job on that. Next, he varied the light source using sunlight, gas flames, electric arcs, among other sources. And lastly, he interposed various gases, liquids, solids between the light source and the receiving spark gap. A very thorough experiment, a very thorough analysis. The interposed materials included metal and glass sheets of various thicknesses, paraffin, shellac, mica, agate, wood, cardboard, paper, oxide, and more esoteric substances such as ivory, feathers, and skins of animals, and so on. And finally, he finds that the radiation that is most effective in increasing the observed spark length lay near the short wavelength limit of the visible spectrum. Okay, and then he further justifies that he then used a quartz prism to disperse the radiation from his light sources. That time we did not have monochromatic lasers. Okay, so after dispersing it from those kind of prisms, the shorter component was found to be enhancing the sparks very well. So that is how he did all those experiments. So you see a dedicated work of Hertz on the interaction of light with metals in certain conditions, causing the spark length in his setup to change. So the experiment, as you have seen, is very, very elaborate. He takes so much pain to take varieties of electrodes and varieties of material to shield and varieties of sources and all those things, and then he disperses the light from a prism, quartz prism, and then separates out the shorter wavelength things, all those things, very, very elaborate, but it is still qualitative, basically qualitative in nature. Of course, the spark length is measurable, and from there you can just say that okay, the effect is stronger or weaker and so on, which shield is more effective, which shield is less effective, which kind of light is actually doing it, and so on and so forth. And but it was still qualitative. So this was Hertz. And then comes another character in our story, and that is Williams Hallwachs. I admit that I could not find many of his original research articles, and I depend only on what others have written about him. But apparently he has again done qualitative experiment to show that yes, the light and shorter wavelength ultraviolet light does affect this is some kind of emission from a metal. And that he has done in a very, very simple manner. Okay, very, very simple manner. And what he has done is essentially he has taken a zinc plate. Okay, so essentially he has taken a zinc plate on some insulating stand, and then it is connected to some kind of an electroscope, some kind of an electroscope or electrometer, and then when this UV light is thrown on the plate, and then he sees what happens to this electroscope. So the first part is that he charges the electroscope with negative electricity or positive electricity. And how do you charge the electroscope? Normally we study in our school books that an electroscope can be charged in two different fashions: charging by conduction and charging by induction. Okay, so if you have an electroscope, let us say an electroscope here, and here are the two leaves, and here is your metallic end, and this is, of course, everything is metallic. This is an enclosure, transparent, so that you can see what is happening here. So initially the two are just hanging. The two are just hanging this way, and if you rub something on the other, dissimilar things, then electrons get transferred from one to. Remember, we are talking of 1887 and 1888 and so on. Alright? An electron has not formally entered into our story. Electron comes only in 1897 when J.J. Thomson completes his series of experiments on cathode rays and show that every material has electrons. Right? We will talk about that in detail, but from today's knowledge, I am just talking of electrons. So when you rub two dissimilar materials, and if electrons are transferred from one to other because of different kind of strengths with which these electrons are bound to the atoms, then the two get charged, positively charged and negatively charged. Okay, if you bring, say, positively charged thing here, if you have a positive charge rod, let us say you have rubbed it and this is positive charge, and that you have brought close to this, remember, close to this. So this is just somewhere here. This is just somewhere here, let us say. What happens? Because of this positive charge, you have electric field, and in the metal you cannot have electric field, and therefore the electric fields will exert forces on your electrons, free electrons, and there will be a redistribution. And the redistribution will be such that negative charges will appear on this side, positive charge will appear on this side. There will be charges on this rod also. How the charges will distribute? The total charge is 0 if you have not made any contact. The total charge is 0, but how positive and negative charges are distributed, that is a tough thing to talk about. Okay, in schools somehow students get impression that if you bring a Q charge here, then correspondingly minus Q charge comes here and plus Q charge goes at the other end, but that is not the case. It's a very difficult story, and the guiding factor is everywhere inside this material, conducting material, the electric field should be 0. So whatever is required for that is how it is distributed. But finally you will have negative charges here, positive charges. If this is positive, then negative charges here, positive charges here, and these positive charges on the two plates will repel each other, and the leaves will spread out. Okay, so that is the explanation, a simple explanation. But remember, what we are talking in our story is before the idea of electron is established. Right. Anyway, so this is it. So this is positive, this is negative. So this whole thing is positive. All right. But if you remove this whole distribution will again be neutralized, and you won't have any charge density anywhere. But if you have brought this positive charge here, and positive charges are appearing here, and negative charges are appearing somewhere here, distribution of course, and now you touch this plate, metallic plate, with your finger. So what happens? So you have touched it and you have provided another path through which electrons can flow, and that we call grounding. Right? Touching by finger, because our body is also conducting and a big reservoir of electricity. Easily electrons can flow into the body or from the body. So when you connect it, you have provided one more path for electrons to flow either from this side to that side or that side to that side. So the positive charges are here, and these positive charges are attracting the electrons. Electrons are coming from here and reaching here, and this is somehow bound to this, and the positive charges are at this end. What it will do is that the electrons will flow from here and will neutralize this. Okay, and this whole plate, the two leaves will not have charge, and they will just be hanging like this. Okay, you can think it in a simpler fashion. Positive, negative charges, if you treat at par, then the positive charges are pushing the positive charges far away, and here we have given another path which is even far away, and therefore this has limited capacity to hold the charge, but this has large capacity to hold the charge. So the positive charges trying to go away from this rod will just flow into this, and this will become neutral. Right? Similarly, if you bring negative charges here, okay, let me first do this. So now it is what you will see, if you touch it with the finger, you will see that these two leaves are again just hanging, they are not spreading. Now what I do is, already some electrons have flown, you still have negative charges here, this is neutral. Now I break this contact, I remove my finger. Now this part is no more neutral. There is a net negative charge on this part, and even when I remove my charged rod, this negative charge still there, and now it will spread throughout to make the electric field zero everywhere, and therefore redistribution, some negative charges will everywhere, negative charges will be here, negative charges will be here, and it will spread. Okay, like this. Now my electroscope is negatively charged, and similarly, if I want to make it positively charged, then what I will do, I will start with a neutral electroscope, and I will rub something on something and ensure that what I am bringing here is negatively charged stick. So if this is negatively charged, it will repel the electrons to go away and reach here, and they will be spread like this. You will have positive charge here and so on, and if you touch it, you are providing the conducting path. These electrons which are trying to go away, they will go away. From here also they will prefer to go into this, and these electrons will go here, and this will become neutral, and they will just be hanging like this. But the positive charges are still here, and when you remove your finger from here, you do not provide any more this conducting path, and remove this also. Then this positive charge spreads everywhere, and then again you have this kind of structure. So this is how the electroscope is charged positively or negatively. It is called charging by induction. We are not touching our stick to this. Actually, my experience is that charging by touching is very difficult, and charging by induction is simple. So what Hallwachs has done is, he does it in three different situations. One when it is uncharged, one when it is positively charged, and one when it is negatively charged. Alright, and in each case he puts some UV light on this, and then sees what happens to these leaves, whether they spread further or whether they go closer. So if it is negatively charged, right, Hallwachs observes that if it is negatively charged to start with, and then you shine this UV light on this, the spread reduces. Alright, so the negative charge here is disappearing. Where is it going? So that is being emitted from here. That is being emitted from here. So that is the kind of experiment he designed, because Hertz has always seen this. Hertz has always seen this, and he had brought about the that as we discussed, UV light causes negative charge to go out of the metal. To show that yes, it so happens, he designed a simple experiment. And this experiment is so simple that we can all do it at our home if you have some kind of a UVC lamp. And I will show it on my table. So friends, here is my electroscope, a glass tumbler, and you can see there are two foils of aluminium which are hanging from a copper hook. And the top of the tumbler is like this. That copper wire from which these two aluminium foils are hanging, they are coming out of that aluminium cover, and that is our say disc. And on this electroscope I'll be rubbing this plastic bottle on my tablecloth, and then I'll bring it close to this. You can see these things have gone separated, and it takes time. Estimate the time it takes to come back. What I had done, I had rubbed it, I had taken the bottle close to the top of the tumbler and touched the aluminium on that cover with my finger. Watch carefully. So it's charging by induction. Okay, so I am going here, then I'm touching, and then I'm removing. So now it is charged, and it takes time to get this charge through air, because there is a humidity. The humidity in the room is 37%. The temperature of the room is 25 degrees. And so you estimate the time, just estimate the time it takes to discharge. So now I have charged it, and now it is discharging. Next I will charge it and put a UV lamp on it. So I am charging it. This is charged. Now the UV lamp is there, and you see it discharges quickly, corresponding to the previous result. So once again, without UV, see how much it stays there. And then with UV, it comes much more quickly. With UV it comes much more quickly. Okay, once again, without UV say it takes much longer time. See, it's taking much longer time. Okay, and with UV starts decreasing much more quickly. So that's the experiment. So you have seen a very simple homemade setup is all that you need to describe what Hallwachs has reported. I'm not very sure if I am actually getting it because of photoelectric effect, because I don't know what kind of charge this bottle contains and so on and so forth, but nevertheless at least it matches with the descriptions of Hallwachs. So next episode we will be talking of work on photoelectric effect by another giant personalities like J.J. Thomson and Philip Lena.